Hello, Ms. Walsh here. So here we go with optimization of problem number 2. All right, consider the manufacture of a cylindrical tin cans of 1 liter capacity, where the cost of the metal used is to be minimized. And this means that the surface area must be as small as possible. Determine the value of R, the radius that will achieve this. Okay, so let's see. Again, you have, hopefully you can see how depending on the radius, you can fit exactly a liter with different sized containers, right? So for example, you might choose a very slim radius, a very small radius, and then have a slim top. And then you can have kind of then a long cylinder. Perhaps that will minimize the amount of material that you use. You would not use exactly the same one. Or maybe it's in your interest to actually use as much to make the radius as large as possible, and then just fill that liter up by having a smaller height. Yeah, so there's different containers you can be creating that contain a liter but use different amount of surface area. Okay, so what we want to do is, again, we want to just write what do we want to optimize here. So to optimize here is going to be our surface area. Okay, and there's the formula for the surface area. You remember that pi r squared is a circle, so this is 2 circles, a top and a bottom, and then you've got your curved cylinder, which is 2 pi r circumference times the height. You don't need to understand the reasoning now, but you've seen it before and maybe you remember. Okay, so let's look at what our constraint is. Well, the constraint is that we must contain 1 liter of volume. Okay, now I've put the conversion here. We're gonna have to go from water in order for the volume. Yeah, we're gonna have to convert it to cubic centimeters. So we know that we need to contain exactly 1,000 cubic centimeters. So our constraint here is that our volume, the formula for which is pi r squared h, remember it's the area of the top times how high it is, and then you've got your, this has to be respected. Yeah, it's got to be, okay, it's got to be exactly 1,000. Okay, so we would love to find the minimum of this function, but right now the problem is we have an h and an r. So what we're going to do is we're going to use our constraint function to isolate for h, which we can then substitute into the equation, and then that will rewrite our optimization equation in terms of 1 variable only. Okay, so we're going to divide both sides by pi r squared. And now our expression for the height is 1,000 over pi r squared. Okay, what we can now do is just take this and substitute it into the function that we are interested in working with. Okay, so our surface area is then going to be 2 pi r squared plus 2 pi r, and then substituting in for the h, we have 1,000 over pi r squared. Now you can simplify. For example, the pi's can be canceled. One of the r's here can be canceled. The 2 can be multiplied by 1,000, but I actually didn't do that. What I did is I've just entered it on the calculator as is. Okay, so let's go to the function. We did the first one, and just be careful, you might get a syntax error. I had to put in a few of the multiplication signs, but there it is. So 2 pi r squared. So please pause this and just make sure that you have entered it like this. You don't need to simplify. So once we plot this, and your plot may look different, basically on the x-axis here are all the possible radii, okay? And then over here we have all the possible surface areas. We're not interested in the negative part of this curve because we can't have negative radii. The domain for this would just be r is greater than 0, right? It must be. And so what we want now is we just want the minimum. In the last problem we maximized, but here we want to use the smallest area possible. Okay, so then just go ahead to your extremum again. And once you've got a nice graph. Okay, and there it is. So I have 5.42, 5.42, and 553.5, 553.581. And remember to always draw a sketch. I actually just realized that I did not draw a sketch on the last one, and that's bad. So we hit, doesn't need to be pretty, but just the fact that we solved it graphically. And if I label my axes here, on the x-axis I've got the radii, and over here I have all the surface areas, okay? And this is my minimum. So determine the value of r that will give this to us. That's this right here. And optimization is very important because you can probably understand that, you know, maybe there's a manufacturer that's restricted by the fact that a certain drink or something must have 1 liter capacity. But obviously, if a manufacturer is producing thousands and thousands of a certain container, then any change in the surface area, the smaller it is, the less the materials will cost him. So the manufacturers are very much interested in this process, okay? It's actually a whole separate field of mathematics optimization. You can Google it and see multivariable calculus with it as well, all right? So there you go. Hopefully that makes sense and is interesting. Ciao.